The final category of reactions that we're going to look at are redox reactions, oxidation-reduction reaction. Oxidation-reduction, oxidation becomes redox reactions. This is a challenging category in terms of balancing, because what this does, in these reactions there's an exchange of electrons. These are the reactions that give us our batteries, give us unfortunately corrosion of metals, rusting of metals. But these reactions, they are two different reactions, an oxidation reaction and a reduction reaction, that have to occur simultaneously to balance the number of electrons. They are two different reactions. Sometimes they are one reaction, but they are two different reactions, as we show in our batteries. In our batteries, we have the two different reactions that occur in separate locations of the batteries, with the requirement that the electrons that are transferred leave the battery and transfer externally to the other end of the battery. So this allows us to power our devices. So to identify if we have a oxidation-reduction reaction, we have to be able to identify if oxidation states, oxidation numbers, are changing in the reaction. So we're going to have a process of identifying oxidation states for reactions. Some are easy. For monatomic ions, the oxidation state is the ionic charge. For elements, the oxidation state is 0. Okay, so we're going to assign oxidation states. So we have to learn how to do this. So the first one, the oxidation state of an element is 0. And it doesn't matter if it's an atomic element, Fe, a diatomic element, H2, or some other version, S8. They all will be 0. The oxidation state of a monoatomic ion is the same as charge. So aluminum 3+ has the oxidation state of 3+. Now the next one is a rule that helps us to identify, harder to identify oxidation states. The sum of oxidation states for a neutral compound is 0. So we have this list on this page here, but this list doesn't cover all the elements. So we're going to use this rule here that the sum of oxidation states for a neutral compound is 0 to help us to identify some of the elements. Along with the next one, the oxidation states, the sum of the oxidation states for polyatomic ion equals the ionic charge on the polyatomic ion. So these two rules help us to identify the charges on elements that aren't otherwise stated in this table. Okay, so group 1 metals, the alkali metals, are going to be a +1. The group 2 metals, the alkaline earth metals, are going to be a +2. Okay, so now we're going to have some rules that won't always be consistent, which means that it's a hierarchical list. So higher on the list is the rule that will prevail. So fluorine in a compound will always be assigned -1. That means fluorine is going to have two values. By itself, the elemental fluorine, F2, will be 0. Fluorine in a compound will be -1. Okay, hydrogen, when we combine it with a nonmetal, we're going to call it a +1. Hydrogen combined with a metal is going to be a -1. So hydrogen is going to have 3 states here. As the element, it will be 0. With a nonmetal, it will be +1. And with a metal, it will be -1. Okay, oxygen, we're going to have a couple of states for oxygen, along with additional states that we won't be able to see in this table, but we'll get when we are dealing with oxygen and fluorine containing compounds. Now, All the numbers so far have been whole numbers, but oxidation states can be fractional numbers also. So for oxygen, as the element, it's going to be 0. In most compounds, it's going to be -2. In a peroxide, it's going to be a -1. We're going to identify peroxides by name. So if you don't see the name peroxide, well, there's going to be one peroxide that I expect you to recognize by formula, and that is H2O2, hydrogen peroxide. But otherwise, O2 does not make it a peroxide unless we have a name attached to it. If we give you a name peroxide, then we're going to say that the oxygen has a value of -1. A superoxide, well, again, by name only, if we see the name superoxide, that would mean a value of -1/2. Don't expect that one. But now here's the other catcher, is that when we have a oxygen with fluorine, the value of oxygen can vary. It could even be positive. So we go to group 7A, 17. These are the halogens. And we already know fluorine is always -1 in a compound. So excluding fluorine, the other compounds, the other halogens are generally -1, except when they're in a compound with oxygen or fluorine. Then they can be something else. They could be fractional or even positive. Group 6A, oxygen group, 16. We're going to expect -2 for these elements. And group 5A, 15, nitrogen group, we're going to expect an oxidation state of -3. We will see, though, nitrogen has a variety of oxidation states in a lot of common compounds because it's combined with other compounds that are higher on this hierarchical list. So, oxidation reduction reactions, redox reactions, transfer electron. So, it's going to transfer electron from the oxidizing reaction to the reducing reaction. The oxidizing reaction is the reducing agent, and the reducing reaction is the oxidizing agent. Let's see if we have a better description. So oxidation. Oxidation. I don't have my description. So oxidation, I'll state mine first one. Oxidation is when we increase the oxidation number. If the oxidation number becomes more positive, we have oxidation. That's it. So oxidation is increasing oxidation number. A lot of people like to say it's the loss of electrons. Well, that is true because electrons are negative. So if we lose electrons, we increase the oxidation number of the element. Reduction is a reduction of the oxidation number. It becomes more negative. That's because it gains electrons, so it takes on electrons. So oxidation produces electrons, reduction consumes electrons. So some memory devices, oil rig, oil. Oxidation involves loss of electrons. Reduction involves gain of electrons. Or the Disney version, Leo says Gur, lose electrons, oxidize, gain electrons, reduced. But now agents flip things, because what agents are things that act on something else. So oxidizing agent is something that oxidizes something else. So the oxidizing agent is being reduced itself. So if it's being reduced itself, it's accepting the electrons. So a reducing agent is reducing something else. So agents act on something else. So a reducing agent reduces something else. So it's being oxidized, which means it's releasing the electrons, donating electrons. So to identify oxidation reduction reactions, if it's not simple, like a single replacement reaction, where we see a element becomes part of a compound. So element is 0 oxidation number in a compound. It has oxidation number of a non-zero oxidation number, so it's a redox reaction. If it's not simple and obvious, what we have to do is identify all the oxidation numbers of all the elements on both sides of the reaction and see which elements change oxidation numbers. If they change oxidation numbers, it's a redox reaction. And if there's no change in any of the numbers, there's no redox reaction. If there's a change in the oxidation numbers, so it's a redox reaction, that means there's going to be two changes. One set will be increasing oxidation number, and the other set will be reducing oxidation number. So these are separate reactions, and they can be physically separated into separate chambers of a battery. So this separate reactions are called half reactions. A half reaction is either an oxidation reaction by itself or a reduction reaction by itself. And since the half reactions, the oxidation and reduction, involve an exchange of electrons, half reactions are going to show electrons. So oxidation reactions are going to show electrons as a product. Reduction reactions are going to show electrons as a reactant. And in a half reaction, we're going to be balancing for all the elements present. We're also going to be balancing for all the charges present. So the charges have to remain consistent before and after the reaction. So there can be no change in charge. And this is what makes balancing redox reactions really difficult. Because if we're trying to balance the reaction overall, we don't see the electrons, we don't see the exchange of charge, but the change of charge is important for the balancing of the reaction. So sometimes without seeing the charge being exchanged, the reaction is almost impossible to balance.